Daniel Rifki bin Zaki Syam, and I am being supervised by Associate Prof. Dr. Nurhayati binti Ahmad and co-supervised by Dr. Habibah binti Ghazali. Next, the content of slides will cover from introduction, problem statement, research objective, scope of study, literature review, methodology, results and discussions, and lastly, conclusion and recommendations. Basically, a typical internal combustion engine produces a high amount of waste heat. This is because in internal combustion engine, about 70% of the thermal energy is released through the exhaust, coolant and surface radiations and to the ambient air as well. The wasted exhaust gas released to the environment can cause air pollution and increase the greenhouse effect. The amount of rejected heat can be recovered up to 40% only. This recovery of wasted heat can only be achieved by using turbocharging technology. However, turbocharger usually operated at a high temperature up to 1050 degrees Celsius, and the material is made of tungsten. As far as we know, tungsten is heavy, expensive, and has a poor thermal insulation. In order to overcome the limitations of tungsten, thermal barrier coating is done by using a new ceramic material which is known as alumina. Next, we will be moving on to the problem background. First of all, which parameters of plasma spraying process could influence the coating thickness and hardness? And secondly, how plasma spraying parameters could affect the performance of coating? Next, the research objectives are to evaluate the effect of spraying distance on the coating thickness by using gas tunnel type plasma spray system. Secondly, to study the influence of spraying duration towards the hardness of coating layer. And lastly, to observe the surface and microstructure of coating layer. Then the scope of study is summarized in table as shown. Firstly, the metallic substrate is 304 stainless steel, which has a dimension of 20 mm length, 20 mm width and 3 mm thickness. Next, the surface treatment used is sandpaper, and the coating substrate used is alumina powder. Then the coating method is plasma spraying, and lastly, the testing is conducted via Vickers hardness test, and characterization is being done by using SEM and EDX. Then we'll be moving on to the literature review. Basically, there are 5 main sources of literature review. Firstly, Akira Kobayashi in 2015 stated that the performance of coating increases by using gas tunnel type system as compared to the conventional type. Secondly, D. Tirumalai Kumarasamy in 2015 stated that the spraying distance decreases when the coating thickness increases. The changing variables are input power and spraying distance. Thirdly, Kandajo in 2017 stated that when spraying duration increases, the porosity will decrease. Then Jia Mingzhou in 2010 mentioned that the coating thickness increases as the porosity decreases. And lastly, Oskan Sarikaya in 2004 stated that when the spraying distance decreases, the micro hardness will increase. Basically, this is the flowchart for the experimental work plan. First of all, we will start from the literature review on alumina, plasma spraying and hardness test. Secondly, the sample preparation, which cover from cutting, grinding and polishing all of the samples. Thirdly, alumina coating is being done by using plasma spraying. However, the main parameters used in plasma spraying are spraying duration and spraying distance. Then viscous hardness testing is conducted in order to evaluate the hardness of a coating layer. And lastly, characterization and microstructural analysis are conducted by using SEM and EDX. In terms of results and discussions, first of all, we will take a look into the growth of aluminium oxide layer on 304 stainless steel substrate. As we can observe, figure 2A represents the cross-sectional SEM of alumina coating layer at spraying distance of 20 mm, while figure 2B represents the cross-sectional SEM of alumina coating layer at spraying distance of 50 mm. Both samples can be distinguished by thickness, as alumina coating layer is observed to be thicker in figure 2B compared to in figure 2A. The coating layers are then further confirmed by using EDX line scan. In this section, we will be discussing on the line scan analysis of sample with spraying distance of 15 and 20 mm. First of all, figure 3 shows line scan at spraying distance of 15 mm, while figure 4 represents the line scan at spraying distance of 20 mm. Basically, the coating thickness can be determined based on the sharp increase of aluminium line intensity as observed in figure 3B and 4B. Meanwhile, the coating substrate interfacial boundary is represented by iron line intensity as shown in figure 3C and figure 4C. Higher thickness is evident in figure 3 as smaller coating distance is more effective because alumina powder can be properly melted and deposited. Next, the percentage of aluminium in figure 3B is higher than in figure 4B. This is due to the fact that there is a formation of coating layer which is denser than the coating produced at longer spraying distance. Next, the temperature of the deposited particle is higher in shorter spraying distance. Then we will be discussing on SEM EDX elemental mapping analysis. Basically, figure 5A indicates the elemental mapping. There are three main elements which have been taken into account for elemental mapping. Firstly, oxygen, which is represented by turquoise color. Secondly, aluminium, which is represented by purple color. Thirdly, iron element, which is represented by green color. Meanwhile, figure 5B indicates each individual element presented in the sample in order to ease the process of identification of each element. Then we will be discussing on the influence of spraying distance on coating thickness. As we can see, figure 6A indicates the average thickness of coating layer at spraying distance of 20 mm, while figure 6B represents the average coating thickness at spraying distance of 50 mm. The average coating thickness in figure 6B is observed to be higher than in figure 6A. This is because when the spraying distance decreases, the temperature of deposited particle will increase. As a result, the deposited particles are thoroughly melted and crushed on the substrate surface. However, when the spraying distance increases, the temperature of the sprayed powder particle will decrease before they are being deposited on the substrate surface, therefore resulting in partial solidification. Consequently, a thinner layer of coating will be formed. Lastly, the influence of spraying duration on coating hardness. As we can see, figure 7 indicates the relationship between viscous hardness and spraying duration. As the spraying duration increases, the viscous hardness increases as well. This is because a thicker and denser coating layer is formed when the spraying duration becomes longer. To further explain the correlation between viscous hardness and the spraying duration, SEM surface morphologies of the coated samples with the highest and lowest hardness were evaluated. Basically, figure 8 indicate the surface morphology of coating with figure 8A and 8B indicate the surface morphology of coating with lowest hardness, while figure 8C and 8D shows the surface morphology of coating with the highest hardness. As we can see, the distribution of alumina coating on the substrate surface is more uniform and thicker for sample with longer spraying duration. This occurs as the majority of flight particles are semi or fully melted in the plasma jet before being impacted on the substrate, forming a dense coating structure and enhancing the flow and compaction of coating during the build-up process. Besides, the value of viscous hardness increases as well due to effective flattening and solidification of the powder particles over the deposited layers. However, if the spraying duration is shorter, there will be a presence of unmelted particles and pores inside of the coatings as shown in figure 8b, therefore leading to a weaker coating bonding strength. Lastly, the viscous hardness values will decrease as the level of porosity increases. To conclude, the reliability and compatibility of new plasma spraying technology, which is gas tunnel type plasma spray system, has been achieved. However, for future studies, improvement of substrate holder should be made, specifically in terms of material selection and mobility, for the purpose of improving the quality of coating and the performance of coating. Lastly, a range of power input and powder feed rate parameters should be taken into account in future experiment in order to provide comparison with the current experiment. That is all from me. Thank you and have a good day.